Have you ever wanted to build your very own machine learning model that is able to play games? Well, in this video, we're going to be doing exactly that. We are going to be building up our very own framework to be able to play different types of web games. Ready to do it? Let's jump into it. What's happening, guys? My name's Nicholas Renaud, and in this video we are going to be building our very own reinforcement learning model to be able to play the Chrome Dino game. So we're going to go through all the steps required to get this up and running. That includes installing all of the dependencies, building up the custom environment, which tends to be the most difficult bit about doing this type of thing. We'll train it and then we're going to test it out. Now, even though we're doing this on the Chrome Dino game, you could take this to just about any other type of web game. The only nuance that you're going to need to take into account is how to define the reward and how to control the different types of actions. But we'll talk a little bit about that as we go through it. Ready to do it? Let's get to it. So Nick, you've done a bunch of ML work with games, but can you actually do it without a pre-built game? Like, say, a random game on the net? Look, we can give it a crack. I'll take it. What's the first step? Well, while there's a bunch of approaches to doing this, we're going to use reinforcement learning. It's a similar technique to what we've used for other games. This time though, we're going to be using the DQN algorithm. And the first step? Well, we're going to need to set up a bunch of dependencies and install stuff. But first things first, let's head on down to the breakdown board. You going to welcome us to it or what? Welcome on down to the breakdown board. So guys, in this video, we are going to be teaching a reinforcement learning agent how to play the Chrome Dino game. Now, there's quite a fair bit involved when it actually comes to actually building this up. Now, the first thing that we're actually going to need to do is set up our custom environment, which tends to be the hardest part in terms of doing all of this. In terms of our custom environment, there's going to be a couple of key things that we need to do because we are going to be using the stable baselines framework. So first up, what we're going to do is create a new environment class. And even though we're doing it for the Chrome Dino game, we could do this for just about any web game, depending on the complexity of the reward function, as well as the complexity of the controls. We're going to be able to get our Chrome Dino game. Actually, I don't like drawing this in red. It's more like, let's give Chrome Dino a gray. So let's imagine our web game here. And let's say we've got a little cactus and our Chrome Dino. That's going to be our dinosaur. So what we're actually going to need to do is implement a function which is able to extract a couple of things. Now, namely, this is going to be wrapped up inside of our web game environment, but our web game environment is going to be hooked up to this game. Specifically, the first thing that we're going to need to do is implement a get observation function. Now, in order to do this, we're going to be using a library called MSS. And this allows us to perform a screen capture. So imagine, let's say we've got our camera. So that is going to be taking photos of our web game, which we'll then be able to apply through OpenCV to do a little bit of pre-processing to get the exact type of frame shape and frame output that we actually want for our deep learning model. So we're going to run that through OpenCV. And then once we've done that, we're also going to need to implement a slightly more custom function. So imagine our game is running. What we want to be able to do is determine when our game is over. So let's imagine game over pops up on the screen. We are actually going to use embedded machine learning or deep learning to be able to extract that out. So we're actually going to be using the Tesseract OCR library. So Tesseract OCR to actually be able to extract the game over text. And this will be able to be used as part of our reinforcement learning environment to determine when the game is done. Now, this is really important because when we actually define our environment inside of the stable baselines and OpenAI Gym framework, we need to be able to determine when the game is actually done. Reward is another really important thing, but we're going to simplify this. So for every single frame that we are alive, we are going to give reward or set equal to reward or set our reward equal to 1. So effectively, we're just going to be rewarding our agent for staying alive. Now, in terms of our reinforcement learning, we are going to be using a library called stable baselines. Baselines 3, and we're going to be taking our environment. So let's imagine our environment as our game with our Chrome Dino. Surely by the end of this, I will be able to draw a better dinosaur. Little arms. We're going to be taking that environment and passing it through to a DQN model. And our DQN is going to learn how to actually play that game. So out of this, what we're going to get is a model which we can then use to actually play our game. So will I be able to have a Chrome tab up with our game actually playing, and this will actually go and run the game and ideally get a massive high score. Don't expect it to be that massive. I didn't end up training the model for all that long, but you get the idea. We'll be able to take our web game, we'll be able to train a reinforcement learning agent, and we'll actually be able to get it to learn how to actually play to maximize that reward. Let's get coding.
Alrighty guys, so we are going to be building our very own Chrome Dino AI. Now we're going to be using reinforcement learning for this, and ideally the end goal should be that we have some sort of model that is able to play the Chrome Dino game. And if you don't know what I'm talking about when I say the Chrome Dino game, you can go to Chrome / and it's pretty much this game. The game where you're basically, the goal is to get the dino to jump above the little cactuses, right? You sort of get the idea. Now, what we can actually do is train a AI model to ideally try to play this. Now, that high score that you can see there of 444, that's actually from the model that I was training last night using AI. So I got to 241, but you sort of get the idea. So the goal is to be able to use a Python model to be able to learn how to play this. Now, admittedly, it does take a little while to train this using reinforcement learning, but nonetheless, we're going to give this a crack and see how we go. So there are 4 key steps or 4 key things that we need to do. That my OCDs kick in, that's not the right size. There's 4 key things that we need to do. So first things first, we need to install and import some dependencies. Then we are going to build the environment. Now, a lot of you have been asking me for this type of tutorial and showing you how to do some reinforcement learning on a completely custom environment. So stuff that doesn't have a pre-built OpenAI Gym framework for it. This is exactly what we're going to be doing in this tutorial. So once we've set up our environment, we are then going to train our model. And then last but not least, we are going to test it out. So first things first, what we're going to go on ahead and do is install and import our dependencies. Now, the first dependency that we are going to need is PyTorch, because the reinforcement learning framework that we're going to be using is Stable Baselines 3, which requires PyTorch. So in order to install PyTorch, we just can hit stable, Windows, or choose whichever version you want. So I'm going to choose stable. You could choose Mac if you want, Linux if you want. I'm going to use Windows. And then pip, I'm going to choose the language that I want to install for, which is going to be Python. And then I'm going to choose CUDA 11.3 because that is the current version of CUDA and CUDNN that I've got installed. Then all I really need to do, let's just double check I'm grabbing the same one that I've got. Yep. So all we really need to do is copy that command and then throw it into our Jupyter Notebook. I've already uploaded this Jupyter Notebook into GitHub, so if you want to go and check that out, let me make sure my Zoom's working. If you want to go and check that out, go to github.com/nicknocknack/DinoAI, and I've actually got the fully written Jupyter Notebook all available there for you, so you can give this a crack and actually test it out. So the end goal will be to be able to get our Dino to actually play this game. So let's give this a crack. So first thing we need to do is install, PyTorch. So I'm going to include an exclamation mark and paste in that command that we just copied from PyTorch. Get rid of the pip or the 3 in pip3. So the full command should be exclamation mark pip install torch, torch vision, torch audio. And then this bit is really dependent on whether or not you've got or you're using a GPU. So I've got a GPU on this machine, so I'm going to use a GPU. If you don't have a GPU, that's perfectly okay, guys. You don't need to stress. So the extra bit is --extra--index--URL, and then it's https://download.pytorch.org/wheel/cu11.3. So that is what drives which version of CUDA we're going to be using. So I can run that command, and I believe I've already got it installed. So you can see it's gone pretty quickly. Now we can take a look at the versions that I've got. So if I type in pip list, everyone usually likes to see this. So where's Torch? So right here, I'm using 1.11.0 plus CU 11.3. So you can see those versions installed there. So I am using the CUDA accelerated version. That being said, for this particular type of training, regardless of whether you use a GPU accelerated machine or not, you're going to get pretty similar training times, at least because we're not doing stuff in parallel and we're not going to get that much of a boost from it. But nonetheless, that is PyTorch now installed. Now, the next thing that we need to do is install stable baselines and protobuf. So let's go ahead and write that command. Okay, so that is our next command written. So this is in, let's just double check that's run successfully, looking good. Okay, so the next command is !pip install stable baselines 3. And then inside of that, I've included the extra command to install all of the extra stuff for stable baselines 3. And then we've also gone and installed protobuf. So this was something actually quite recent that I noticed I had to have installed. There was a change in the protobuf package, which I believe is used for the training of the PyTorch model. So just keep that in mind that you've got to install, or at this moment, I'll update the notebook if it does change. So equals 3.2.0 or 2.3.20. And then an asterisk. So this sort of gives us a version within 3.2.0. Or 3.20. Oh God, I don't know why I'm saying that wrong. All right, so we've now gone and installed stable baselines. And for those of you that haven't checked out any of my previous stable baselines videos, so stable baselines is an absolutely amazing, reliable reinforcement learning framework. So think of it like the scikit-learn of the reinforcement learning world. It is really, really good, particularly when you're trying to do hardcore reinforcement learning problems, because you don't need to write them yourself from scratch. So that is stable baselines now installed. Now, in terms of how we're actually going to work with Chrome Dino, this is one of the funnest things one of the most fun things that I've actually done as of late. So to capture the Chrome Dino frame for our game, we're going to be using OpenCV, so that's not an issue. To send commands, we're going to be using a library called PyDirectInput. And this allows us to actually use Python to actually send commands, and it's very, very quick. And that's a huge advantage when it comes to working with reinforcement learning. You want it to be fast. Then the other thing that we're going to be doing, which is my personal favorite, is that you can see that right now we've got this game over tab over here. Now, what we want to be able to do is once an episode finishes, so think of an episode as one round, we want to be able to detect when that round is over. We're actually going to be using optical character recognition to detect when this game over sign pops up. Now, because we're not going to do too much pre-processing, we're really just going to detect the game section, but that's perfectly fine. We're actually going to set up a function that determines once this game over pops up. So we've got to bring in, or we've got to install a bunch of stuff to be able to do that. So for the PyDirectInput, we're going to install PyDirectInput. For the OCR bit, we are going to be using PyTesseract, which is Google's OCR tool for Python, which is pretty cool. So you got full-blown detailed installation instructions available on the site. So if you do get issues with my installation, then you know where to come. But really, it should just be a PyInstall PyTesseract. Coolio. But there are also some dependencies. So what do we need? So we need at least Python 3.6. You need PIL to be installed. You need to install Google Tesseract OCR. So if you actually go to that, it's actually going to walk you through how to install all of this stuff. Is this really just a pip install? I don't actually remember installing this, but I must have installed it at some stage because it looks like it is working. Oh yeah, so you can install it via the pre-built binary. I think this is what I ended up doing. Yeah, so you could just go to the binary over here. So download the Windows equivalent and then run through this. So make sure you got Tesseract OCR installed to begin with, otherwise you're going to have a bad time. Then we're just going to install the Python, effectively, what is it, like a wrapper to be able to use that. So let's go on ahead and do this. If you need more installation, I'll include links or more info on the installation for Tesseract. I'll include links in the description below, as well as some other good YouTube tutorials that show you how to install it from scratch. Okay, but for now, what we're going to go on ahead and do is just install the Python component. So we are going to include !pip install and then install those last couple of libraries. Okay, those are our last couple of libraries now installed. So we've gone and written one line, and that is !pip install MSS, PyDirectInput, and PyTesseract. I think MSS was for PyDirectInput, input. It was either for PyDirect input or PyTesseract. I think, oh yeah, so wait, we're using MSS for the screen capture. So that's actually what allows us to capture the screen. So MSS is being used rather than, I thought we were using, what was it? OpenCV, we're clearly using MSS. And there was actually a great YouTube tutorial that I watched recently that showed that MSS was faster than OpenCV. So hence, that's why I ended up bringing it over into this. But keep in mind, there's a bunch of different ways that you can do that. The PyTesseract bit is also optional. I saw another guy doing it using, looking at the overall color in that particular region rather than trying to actually extract the text. So bunch of ways to do this. This is my way. There's a bunch of different ways that you could actually go about this. But this is the way that I also wanted to teach you, not necessarily just my way. Okay, so what do we got? Got some installs. So we're installing PyTorch, installing stable baselines, and then installing all the stuff that we need to be able to extract a frame, which is what we're going to use MSS for. PyDirect input is going to allow us to send commands, and PyTesseract is going to allow us to extract the game over component. So we've installed all of those. Now what we need to do is import them into our notebook. So let's go on ahead and do that. Alrighty, those are all of our dependencies are now imported. So we've gone and imported MSS, and MSS is going to be what allows us to actually capture the screen. So it's ridiculously quick. Let's actually make some notes of this. All right, so MSS used for screen cap. PyDirect input is going to be used for sending commands. And this is effectively telling the game or passing commands to the game, right? So it might be WASD, might be pastoral click, might be up and down. For Dino, it's pretty easy. It's literally just jump up or jump down to, or duck down to dodge the birds. You sort of get the idea. OpenCV, I can't remember exactly what we're using that for, but we'll see it soon enough. So OpenCV allows us to do frame processing. NumPy is just a transformational framework. Let's actually walk through these commands. So the first one is from MSS, import MSS. So that's our screen capture. Then PyDirect input. So import PyDirect input. Then we're bringing in OpenCV. So import CV2. Then we're bringing in NumPy. So import NumPy as NP. And NumPy is just great for working with a bunch of different types of arrays of different ranks. So that definitely helps us out. Then we are bringing PyTesseract for OCR. So that line is import PyTesseract. So we are bringing this OCR for game over extraction. We are then bringing matplotlib to visualize frames or captured frames. And that line is from matplotlib import pyplot as PLT. So that's bringing matplotlib. We are then bringing in time or pauses, and that line is import time. So between when we actually send commands and while we actually wait for the frame to change, so we're going to bring in time. So this gives us a little bit of leeway when actually going between different actions within our game. So I've used this in a bunch of places to actually perform pauses. So just keep that in mind. It's really just to take a little bit of a sleep, have a nap. And then we're bringing in our environment components. So the first one is from Gym import env, and this is going to be the base class when actually defining our own environment down here. And then we've brought in a couple of different types of spaces, and for this we've brought in from gym.spaces import box and discrete. So box is going to be used to extract or to represent the shape of our game input, which is just going to be an image. Discrete is going to be used to represent our possible actions within our reinforcement learning environment. Now, remember, a reinforcement learning environment is all to do with 4 different things. So if you remember Area 51, agent, reward, environment, and action. So we need to define all of those in order to have a valid environment. So we're going to be using our spaces down here to be able to define that. So those are our inputs. So MSS, PyDirect input, OpenCV, NumPy, PyTesseract, matplotlib time, and then we've brought in a bunch of stuff from OpenAI Gym. That's pretty much all of our dependencies installed and imported now. So it doesn't look like we got any issues there, but the only one that I can think of which might be a little bit tricky is PyTesseract. So I'm going to link in some additional stuff in the description below so you've got that sort of covered. But for now, that is our setup all done. Let's jump back on over to our client and have a chat.
Alrighty, so that's the 1,000,001 dependencies now installed. What next? Well, this is where the magic happens. This isn't gonna turn into one of those close-in magic videos, is it? So, we're going to be building the environment for the ML model. This is what allows the machine learning model to interact with the game. This is the hardest part about training reinforcement learning models for games. It's often done using different types of architectures, which include virtual machines and containers to scale how fast we can train. Got it. We keeping this simple or what? Sure are. We're going to use the OpenAI Gym framework to do it. Let's roll.
Alrighty, so now that we have our virtual environment now installed with all of our dependencies and all of the frameworks that we're going to need, we are going to go on ahead and build our environment for reinforcement learning. Now, our environment that we're going to be creating is going to be called a web game environment. So we are going to create a new class and we're going to call it web game. And we are going to pass through our base environment from OpenAI Gym. So we're going to pass through env there. Now, there are a bunch of different methods that we need to implement for a base environment when working with OpenAI Gym. So the first one is the init method. And we're just going to define these initially for now. We're not actually going to write them out. So we're going to set that to pass. The next one is step. And typically to that, you pass through an action. So the init method is sort of where you do all your setup and you define all of your different environment variables, what your environment actually looks like, so the shape, so on and so forth. The step is actually what gets called, right? So let's say, for example, you want to take an action inside of your game. So let's say, for example, you're playing COD or you're playing, I don't know, Fortnite, and you wanted to strafe right or strafe left. So actually moving to the left and moving to the right is actually an action. So in terms of actually passing through an action to our game, we can pass that action through to step. Now, how we represent that can be done in a whole bunch of different ways. We're going to take it pretty simply and have, I believe, 3 actions. So do nothing, jump up, or just go down. Now, we'll play around with this in a second, but just know that init is where you set up stuff, set up the environment and action and observation shapes. Step is what is called to do something in the game. And typically you get a reward, the next observation, any information, as well as whether or not the game is done. So that's the return out of your step environment. Then we typically also have a render function, def render, self. And this allows you to visualize the game. Not all that important for ours because we're actually going to have the game on the screen. So that's perfectly fine. And then we also have a reset function. So almost like restarting the game. And we are also going to need to implement a couple of custom functions as well, or custom methods. So we are going to implement one called def get observation. And that is going to be called to get the output of our game. So we'll actually pre-process, or over here, we'll actually pre-process and get a specific region out of the Dino game. So we might get, I don't know, like 100 pixels by 100 pixels just to cut down, because we don't really care about looking too far forward. Although that might be an optimization that you choose to do later on. It's definitely something that you could do. So this is going to get the part of the game that we want. Get at the observation, it's pretty much part of the observation of the game. And then we also want a get done function. Get the done text. Get done. So this actually checks whether or not the game is over. So whether or not we've actually got game over being displayed on the screen. So we will be able to check that out. Okay, so those are our 1, 2, 3, 4, 5, 6 functions. Let me check. Step, reset, render, close. Oh, we also need to close. So close, this closes down the observation. OBS, oh gosh, I can't type today. So def, close, pass through self, and pass. Okay, so those are our 1, 2, 3, 4, 5, 6, 7 different methods that we're going to need to fill out. Now we're going to take this one step at a time, so you'll see how each one sort of gets built up. So we'll probably do init first, and that will set up our initial game. What we'll then do is we'll probably take a look at the get observation, get done, and we'll probably need to do steps sort of simultaneously. But for now, let's first start by setting up our initialization function. So here we're just going to make sure we initialize the base environment as well. And we're also going to set up what our action and observation shapes look like. So let's do this. Okay, that is the beginnings of our init method. So we've gone and written 3 lines of code there. So the first one is subclassing our model. So we're calling super dot underscore underscore init underscore underscore and then open and close parentheses. So this allows us to use the base class. Then we are setting up our spaces. So these are really, really important whenever you're defining any reinforcement learning agents. And I'm going to walk through this. You'll probably see this being referred to a bunch of different times. So the first thing that we've actually gone and defined is the observation space. So self.observation space equals box. And then the low value inside of our box is going to be 0. High value is going to be 255. This is really just saying we're going to have a multi-dimensional array as the returned output, right? So that is all that it's saying. So box is sort of a little bit more of a free form shape. So you could have images. Typically you'd use box for images. You'd use box for time series data and a whole bunch of others. And then we're specifying our shape. So our shape is going to be one batch, and then we're going to be 83 pixels high and 100 pixels wide. And the data type is going to be numpy u into 8 because it's a very small and compressed data type, which we like. And that is our observation space. So basically we're saying that we're going to give back an image. Our action space is going to be discrete 3. Now we are going to have 3 different actions. So spacebar, which is jump up, 1, which is down, and then the third action that we're actually going to have is no operation. So inside a step, we're actually going to define an action key here. So action key. So action 1 and discrete is really, let me actually show you. So actually, I'll show it to you once we actually create an instance of this model. So 0 is going to be spacebar. 1 is going to be is going to be duck, which is down. And then 2 is going to be no action, commonly referred to as no op. Cool. All right. What have we done there? So that's fine. So that is open. Positional argument follows keyword argument. We need an equals here. Boom. Okay. Let's see if we can create an instance of this class. I don't see anything let's get rid of that pass for now. So if we said env equals web game, okay, no issues. So if we went env.actionspace.sample, this is exactly what I wanted to show you. Okay, so you can see here that when we're creating when we're running action space, we're getting number 2. Now, what we're going to do inside of the step function is we're going to map number 2 to no action. So this means that we're not going to do anything, right? So our agent will just keep running forward. Our little Chrome Dino won't do anything. Now, if we go and sample again, we're getting action 1. Action 1 is going to be duck. So typically you want to duck when you've got birds coming at you. Action 0 is going to be spacebar. So if we sample again, so we're getting action 0, which is going to be a spacebar, which means that our little agent is going to jump. So this is pretty common whenever you're working with other environments, and you've probably seen me use this a bunch of times before whenever I'm building reinforcement learning models. So the action space typically defines what actions you can pass to the game. env.observation_space.sample is going to be a representation of the image. So you can see that that's the image. Now keep in mind we imported matplotlib, so we might be able to go plot.imshow. Let's see if this works. Doesn't look like it wants to. Let's grab the first value. There you go. So that's what our image is actually represented as right now. So obviously it's a bunch of random values because it's just creating random values whenever you're whenever you're accessing the observation space. But for now, just know it's a bunch of random values at the moment. Eventually, we are going to be representing this as a set of values from our Dino, right? And you can see it's 80 pixels high by, 100 pixels wide, or 83 pixels high by 100 pixels wide. That is that representation there. So 83 pixels high by 100 pixels wide. Cool. All right. So we've now gone and defined what our spaces look like. Now we also need to define some classes. So we want to define our MSS class. We also want to define where our game location is. So what positions we want to extract from the frame. So let's go and set these up. Okay, so we've gone and written another 3 lines of code there. So let's zoom in on that. So the first one that we've gone and written is self.cap equals MSS. So if you actually go to the MSS library, Python. So it does allow you to create cross-platform screenshots. Now, typically you're defining MSS as a first instance, and then I think we're using the grab method to be able to grab captures from our actual frame. There you go. So this actually allows you to grab specific areas of the frame, and we can define the regions as top, left, width, height to be able to grab a specific area of the frame. So we don't need to grab everything. We can actually grab a specific area. And this is the next line, or this brings us to our next line. So keep in mind, the first line that we've written is self.cap, and we're setting that equal to the MSS class, which we imported right back up at the start. Then we're creating a new attribute, so self.gameLocation. So this is going to be the entire area of the game that we want to potentially extract. And we're specifying this as top equals 300. So this is the region from the top, and then how far in we're going. And then we're grabbing everything from the left. So we're going to go down 300 pixels and go from there. We're going to go all the way from the left, and we're going to extract 600 pixels wide by 500 pixels high. So this basically just defines the region. So self.game.location is just defining the region that we actually want to go and extract. Likewise, we're doing the exact same for the done location. So self.done location, and then we're actually getting back the region that represents where done is. So top is equal to 405, or top, so we're going 405 pixels down, and then we're going 630 pixels from the left, and then we're grabbing 660 pixels wide by 70 pixels high. So that defines where that done section is going to be. Now, what we can actually go on ahead and do is actually set up our get observation and get done functions, because we've sort of defined the stuff that we're going to need to be able to define those. So really, we're going to grab that capture, and we're then going to pass that through to cap.grab. We'll pass that self.gameLocation to be able to get the region of the game. Now, when we actually go and run this, we're actually going to take our Jupyter Notebook and sort of run it like that. So we've got our Jupyter Notebook running here, and then our game running in the background, so we can actually have them running simultaneously, because that's what we're going to need. So that is our init method now done. So we've gone and subclassed our model. We've gone and set up our spaces. And remember, we set up our observation space and our action space. And then we also defined our extraction parameters. So we defined the MSS class because we're going to use the .grab method to be able to grab our frame. We've defined our game location and our done location. And I also showed you pretty sneakily how to actually create an instance of this environment. So I've written env equals web game, and this is just creating a new instance of this class up here. And then we can use env.actionspace.sample to sample our actions. Boom, 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 boom. And then we can use env.observationspace.sample to sample our different, or our observation space. So, and we've also used matplotlib to be able to visualize that. And right now it's just a bunch of random values because we haven't actually gone and effectively grabbed our observation, but we can do that. So let's actually go and do our get observation function first. So we're going to use the get observation method inside of this step to be able to get the capture of our game. So we actually want to be able to go and extract this and maybe do a little bit of pre-processing. That's where we're going to use OpenCV. So let's start defining this. Okay, so that is the initial line for our game, and we're going to take this one a little bit more step by step than usual. So the first thing that we're doing is we're grabbing a raw screen capture. So let's actually remove all this stuff to begin with, and let's see what the completely raw capture looks like. So we are running self.cap.grab, which is using our MSS line over here to be able to grab the screen capture. And then to that, we're passing through self.game_location. So this is going to allow us to get our initial screen capture. So if we actually go and run this, create a new instance of our game. Now, if we actually run env.getObservation, let's see if that works. So it looks like we've got a screenshot. Now, what we actually need to do is extract the value from that. So I believe we can use mp.array to grab it. Let's try this. And that is a NumPy array representation of our getObservations function. So now if we pass this through to plot.imshow, maybe we can grab our game capture. Keep in mind, this is going to be from our current screen, right? So right now it's grabbing the code. So it's very meta. But if I move this over to this side, moved our notebook over and brought it back up. Wrong one, this one. So if we go and ran this again, so we're now grabbing our frame capture for our game. Pretty cool, right? Now, right now it is pretty big. So we actually want to compress this down to be in the same shape that we had over here. So 83 by 100 pixels. So we're actually going to compress this down a little bit because right now it's pretty big. You want to compress your image sizes down when actually working with a DQN algorithm. So compressing it, passing through smaller frames is going to serve you a lot better in the long run. So we actually want to return np.array. So remember, we actually wrapped it inside of the array to grab the actual pixel values. So now if we run this, we can get rid of numpy.array here. All right, so rerun that. Boom. Okay, so we're already getting our frame. If we move this bad boy over. Right, so we're getting our Chrome Dino. Let's move this. Let's bring this first. Right, so we're getting our Chrome Dino each and every time. If we went and played a little bit, you can see that is exactly that. So we've now got a array representation of our frame. Pretty good, right? Okay, so the next thing that we actually want to do is we want to convert this into a NumPy array, and we want to convert the data type into np.uint8. So we want to get that done because right now it is not np.uint8. Let's take a look. Let's see how it's represented. Oh, it already is uint8, so we don't actually need to do that transformation. So we're actually okay there. So let's leave that for now. We don't actually need to go and do anything else there. Okay, so once we've done that, the next thing that we do want to do, however, is we actually want to go and reshape this. While we're at it, let's just double check the shape. So we are 500 by 600 by 4. We don't actually need 4 channels, and I wonder if this is an output of MSS. So let's go and grab the last 3 channels rather than 4. So if we go all channels, all so all, all height, all width, and then let's grab the first 3 channels, see what that representation looks like. Pass it through plot.imshow. Okay, that's still looking okay. So there must maybe be an alpha channel coming out of MSS. So if I go and run that again, still looks good. Let's take a look at our data type. np.uint8. All right, so we're looking good. So if we didn't have the correct data type as well, just by the way, we could type in .astype and then np.uint8. We go and run that. So again, we're uint8, but we can actually drop that. We don't need this because it's already returning the correct data type. Boom, uint8. Okay, so that's looking good. So we've now got our raw screen capture. So we've gone and written self, or let's actually take the full line. So raw equals np.array, and then to that we are grabbing or using our MSS screen cap from over here. So we're running self.cap.grab. Let me zoom in on this so you can see that. So self.cap.grab. And then to that, we are passing through the game location. And remember, the game location represents where in our screen we actually want to capture. And then we are wrapping it inside of a NumPy array to actually extract the pixel values. And then we're just grabbing the first 3 channels because I believe there might be an alpha channel or I don't know, a specific 4th channel that's coming out of MSS. We only want the first 3 to actually allow us to work with OpenCV to reshape it and whatnot. Okay, so that's the first line done, and that's probably the hardest to sort of get your mind around. Now it's just a little bit of computer vision pre-processing, and that is our observation bit then done. So let's go and finish our get observation method. Alrighty, that is our get observation method now done. So I've gone and written 3 additional lines of code there. So the first thing that we're doing is we're grayscaling. There's a typo there already. So I've written gray equals cv2.cvt color. We're taking our raw output, which I walked you through, and we're converting it from BGR to gray. So this is just a channel color conversion code. So rather than having a color image, which we don't really have color in here anyway, so we're going to focus on dropping it down into a single channel rather than it being 3 channels. So we're going to make it a gray image. Then we're resizing it. So we're resizing it to be 83 pixels high by 100 pixels wide. So cv2.resize takes in width first, then height. Now, a NumPy does it slightly differently, just a key thing to keep in mind. So resized equals cv2.resize. We're passing through our gray image, and then we're passing through the height and the width and then the height, so 100 by 83. And then we're reshaping it so that we have channels first, because that's the format that PyTorch and stable baselines actually wants it in. Stable baselines, not necessarily PyTorch. So I've written channel equals mp.reshape. We are passing through our resized image to that. We're specifying that we're going to have a channel first, and then we're going to be 83 pixels high by 100 pixels wide, and then we're returning channel. So if we go and run this now, we go and get our observation. We've got our observation. If we go and run plot.imshow, it's going to throw an error. If we get that, reduce the first channel, boom, that is our image representation. Looks terrible right now. Let's actually go and grab our Dino. Boom, that's our Dino representation. Pretty sick, right? So we've now gone and grayscaled down. We're getting our image successfully. And if we wanted to go and convert it properly, so we could type in cv2.cvt color, CLOUR, and then pass through that observation. And I think if we go cv2.color underscore BGR to RGB, maybe. See what that looks like. What have we typed in there? We haven't typed that in. RGB. Okay, there we go. That's looking better already. So if we go and run this, there you go. So that's what our actual representation looks like. So I've just gone and passed through the color conversion code to work with matplotlib. But we've now successfully actually gone and got our frame out. Pretty cool, right? Now, we're actually going to use this get observation function inside of our step method. So we're actually doing the most involved bits first. So once we've gone and done this get observation bit, we know we can extract our observation. The other thing that we need to do is be able to extract our done text. So you can see that we've got game over there. So we want to be able to extract that as well. So we're successfully getting our observation. Let's actually move this down because this is pretty useful. We don't need the sample bit anymore. We don't need the action space anymore. We'll come back to that. So the next thing that we want to do is we want to go and use OCR to be able to get our done text. So let's go on ahead and do that. So we are actually going to use PyTesseract for this. Okay, so I've just gone and quickly written 2 lines of code there. So I've written done cap equals self.cap.grab. Remember, this is using MSS again to be able to grab our done screen, and then we're passing through done location. So remember, in our get observation bit, we used self.game location. For our done method, we are using self.done location, which was defined over here. Now, if you're doing this on other games, you might need to tweak these 2 parameters to be able to get the specific regions of the screen that you want to get. So I've already sort of predefined this to make your life a little bit easier. But if you're doing something like, I'm trying to think of a game. We played around with Timberman. We might specifically have Timberman in a specific section of our screen, and we might point our game location to that, and then our done location to a specific other region to be able to determine whether or not a particular episode is done. So defining these are really important. And I've sort of just taken a little bit of the hassle away for you to be able to know where to get it from. Okay, what have we gone and defined here? So we've now gone and defined where our done component might be. So let's actually minimize that bit for now. So if we actually go and run env, or let's actually reinstantiate our environment, env.getDone, it's just returning our screenshot. Now if we wrap this in a NumPy array, you can see we are now getting our array values back. And if we wrap that inside a plot.imshow from matplotlib, we're getting a black bar region. Now if we move this over to the side, let's try that again. So you can see that we're getting game over. I don't want that there. I want it around about here. Boom. So you can see that we're now getting the game over region. So we've now successfully gone and grabbed that text, but we haven't determined what is actually in that region. Because let's say, for example, bring it back up quickly. So let's say, for example, I went and ran this right now. I'm not actually going to have anything inside of that region which represents game over. So we actually need to do some sort of detection to determine whether or not the game is actually over in that particular or at that particular time step. And this is where PyTesseract is going to happen. So before we forget, let's just wrap this in a NumPy array to actually extract the picture values. And remember, this shape is going to have that fourth channel as well, right? So let's type in .shape. Yep, so we just want the 3 channels. So we're going to go at the end of this. So we've closed the NumPy array. No, we haven't. So let's close that. And then we want the first, what is it? The first, all of the height, all of the width, and then we want the first 3 channels. So that is that done there. So let's go and take a look at that again. So if we go and run env.getDone now, boom, we've got 3 channels. Let's just move this over to the side. And then if we run, well, my head is probably covering that, isn't it, right now? Let's bring this up a little bit. So env.getDone, and then if we type plot.imshow, you can see that that is grabbing that region. Let's let it get done. Get done. Boom. So you can see we've at least got game over. If I move this over a little bit more, boom, we're getting game over. Cool, right? Okay, that is looking good. So what else do we need to do? We now need to do the PyTesseract bit. So actually do the OCR on this region. So because PyTesseract is a little bit finicky if you don't do pre-processing, we're actually going to just take a look at the first 4 values within our text. So we're actually going to go and just define a list of strings that are valid. So valid done text. And we're just going to focus on the game bit. So I'm going to create a new variable called done strings. And if you wanted to do more pre-processing and play around with PyTesseract a little bit more, you definitely could. I just found giving it a few options is a little bit faster. So what I noticed when I was actually testing this out is that it would read the game text for Chrome Dino as game or GAHE. So rather than specifying for, or rather than forcing Tesseract to look for game, I'm just going to say, look, if it's either game or GAHE, consider that done. So we're going to grab the first 4 letters that PyTesseract extracts. So let's go and do this extraction, and then we'll be able to wrap this up, or at least wrap the get observation and get done functions done. Okay, that is our OCR bit done. So we've now gone and defined a new flag. So I've just set done equals to false. So initially we're going to say our episode is not done until we go and validate whether or not we've detected game or GAHE inside of our game over area. Now, the reason that I don't look at the over bit is because for whatever reason, PyTesseract does not like this V and does not like this E. So it reads it in too many variables to actually count. Now, again, you could go do like some dilation and some other pre-processing to actually force it to look a little bit better, or look like the text it actually represents. In this case, just doing it this way is way faster. But you could definitely go and fine tune this and do as I say, not as I do. So you could definitely make this a lot better. So then what we're doing is we're defining a new instance of PyTesseract. So we're going to save the value out of the image to string method inside of a variable called res. So I've written res equals PyTesseract.image to string. So this is the function that actually does the optical character recognition. And to that, we're going to pass through our done capture. So what we had from over here to that. So effectively, this line is looking at that game over region and it's trying to extract any text from that to a string. So then what we're doing is we're grabbing the first 4 letters, which ideally should represent game, and we're double checking whether or not that string that's been extracted from here is inside of this array. So if the string that's been extracted is game or GAHE, then we're going to set done to true, which effectively means later on we'll end our episode. So we'll cut off our AI there, or the training of that episode there. And then I've specified a return, or we're going to return the done value. So whether or not true or false, it's done. And we're also going to return our done captcha just so we can visualize that. So let's actually test that out now. So if I go and run our web game environment again, so let's run this. So our visualization still looks the same, but now let's just bring this up here a little bit. Right? And if we now go and run get done, this is going to return 2 values. So hold on. Okay, so it's running. So you can see it's detected true. So that's good. So let's just say this is done, and then this is done cap equals env.getDone. So this is saying that we have in fact finished the game. So it's returned. It looks like it must have detected game. And if we go and visualize our done cap, plot.imshow, done cap. Boom. So we're detecting game over. So in that particular, if I move this over a little bit more, I know it's a bit of a pain. I'm recording on one screen, but you sort of get that. Let me zoom out. Maybe you'll see it. Oh, that's much better. So if I go and run that, looks like it's detected game over. Bring it over a bit more. Boom. All right. So you can see that that has definitely detected game over. Let's actually return the res value as well, just so we can see that initially. So we're going to return res, which should be the PyTestRact text. So let's go and redefine that. So our OCR has detected game. Pretty sick, right? We've gone and detected the game over region, and we have gone and set done equal to true. So that is our done captcha now done. All right, so that is looking good. Let's zoom back in. We don't actually need to return the res bit. We're not going to need that for our game. So that's just extracting our code at the moment. Not all that useful. We've gone and extracted our done and done cap. Boom. Boom. Okay, so now actually this is a good test, right? So you can see that right now we're currently just grabbing the black text from our code editor, which is a Jupyter Lab notebook, and you can see that it has not detected done, and that's because there's no done on the screen at the moment, which is a good sign. So it is actually working well. Okay, so what have we done? So we've gone and now defined our get observation method and our get done method. We've also gone and set up our init method. All that's left to do is wrap up our step, render, and reset and close method. Okay, so still a little bit to do. So first things first, let's go and wrap up our step method, because that is quite possibly the most important method. So the first thing that we're going to do is we're going to map our action to an actual key. So we're going to create a new dictionary called action map. And we're going to say action 0 is space. Action 1 is going to be down. And action 2 is going to be no op. So we can now use that as like a translator between our discrete space, which remember just returns 0, 1, or 2, to be actually able to represent an action. So then what we can actually do is use the PyDirect input method to actually go and trigger an action. So we're going to say if action doesn't equal 2, so as in it doesn't equal no op, then actually pass through the action from our action map, right? And to do that, we can type in PyDirect input dot press, and then we're going to pass through our action map and then the actual action that we are getting from over here. So inside of our step method, we're actually going to be passing through an action. So this is actually going to do something to our game. All right, that's looking good. So that's our action taken care of. Then what we want to do is define so we want to double check whether or not the game is done. So to do that, because we've got our get done method, this is going to make our lives pretty easy. So we can go done, comma, done cap equals self.getDone, get done. So that's going to tell us whether or not we're done or not. And then what we're going to do is we're going to return back the new observation. So new observation equals self.get observation. And then, so the way that we're going to define our reward, so let's actually just make some comments. So this is checking whether the game is done. Get the next observation. Actually say next observation. We'll just say new observation, whatever. You sort of get the idea. And then, so that's those two done. Then our reward. So we're just going to say for every second or for every frame we're alive, we're going to reward our agent with 1. So reward. And this is pretty simplified, but you could definitely go and make this a lot more sophisticated. But keep in mind, the way that you get a high score in Dino is by staying alive. Now, if you stay alive, then we should be rewarded. Hence, we're just going to set the reward equals to 1. So I'm going to say reward equals 1. Now, this basically means that we get a point for every frame we're alive. Cool? Cool. So let's quickly go through that again. So we've gone and defined our action map. Now, remember, when we call step is what we do every single frame of the game. So it's like taking an act, looking at the observation and doing something. That's effectively what our AI is going to be doing. It's going to look at the game and go, hey, what's the next best action? It's going to pass action to the step function. And then our action map is then going to map through a 0, 1, or 2 to either the space bar or the down bar. If there's 2 return, then it's not going to do anything. And in order to actually go and press that button, we're going to use PyDirect input.press. We're going to pass that action through our action map. So it's going to translate a 0, 1, or a 2 to a space or a down. Then we're checking whether or not the game is done, and we're going to grab the new observation, and we're also going to reward our agent with a 1 if we are still alive. We are also going to return an info dictionary. This could have just about anything in it. I just normally set it to blank unless I really need something, because that is what the stable baselines framework expects. And then we're going to return stuff. Order is very important here. So we're going to return the observation, which is new observation. We are then going to return our reward, which is just going to be 1 if we're still alive. We're going to return whether or not we're done, and we're going to return info. Cool. That is our step function done. So let's zoom out a little. So we've now, inside of our step method, we've gone and defined our action mapping. We've gone and defined whether or not we're done, and we've grabbed our new observation. We've gone and defined our reward, which is just going to be a 1 point for every single step we're alive. If you wanted to, you could also maybe do some OCR on this value over here. So maybe extract the 42 values. It doesn't really matter. We can define our own reward because it's in relation to our agent learning anyway. But for more sophisticated games, you might actually want to extract the value. Let's say, for example, you're playing Forza and you wanted to extract lap time as a metric for how fast or how good your AI is. You could definitely go down that route. And then we've defined an info dictionary because that is what stable baselines wants. So that is that now done. I think we're looking good there. So what else do we need to do? So we need to do our render and our close. So these two are pretty much aligned to each other. So let's do these. So our render is just going to use OpenCV to show our screen. So cv2.imshow. We are then going to pass the current frame. So we haven't actually gone and set that. So, all right, let's do that. So over here, so rather than, what we can actually do is just type in self.cap.getObservation. Wait, no, self.cap and then self.game location. So we could do that. Actually, we don't even need to do that. We can just pass through. So self.getObservation is going to grab back that value anyway. We could probably just go self.getObservation. And maybe this works. So cv2. What is it? .wait key. If cv2.wait key. So basically we're checking whether or not we're giving ourselves some time to render. And 0xff equals odd q. And then we're going to close. Let's check whether or not that works. We need, where's our render? adding a column there. So I've just written cv2.imshow. So we're going to show the game frame. And to that, we are going to pass through self.getObservation, which should get our observation from here. We could also set, so I realized that previously what I'd actually done is I'd gone and saved the current frame as a variable inside of this, but looks like I haven't done it this time. So that's what I've done in the past. Then we're double checking whether or not we've hit Q on our keyboard. And if we have, then we're going to close down our frame. So if I go and run this, render or run env.webgame. If I type in env.render, no, we've got an error. SCN is 100. That is not happy. All right, so we've got an issue there. Let's try to close that down. Doesn't seem to want to close. All right, let's double check this. Let's try self.cap. And then what are we going to do? Self.game location. And then pass through a NumPy array. So maybe it doesn't like the fact that it's grayscale. I don't know, maybe. We're going to convert it into a NumPy array. And then we're just going to grab the first 3 channels. So bang, bang, and then first 3. Try that. Still doesn't like it. MSS object is not callable. We need to run self.cap.grab, don't we? Okay, that didn't throw an error. All right, so that looks like it's rendering now. So we should be able to hit Q. Doesn't like that. Anyway, at least we've got part of a render function. Doesn't look like it's the nicest render function, but you could definitely go and do that. To be honest, the render function, I know I'm sort of getting an out here, but the render function doesn't matter all that much because we've got the game playing live, but you could definitely go and extend this out a little bit. I've sort of just gone and written this on the fly here, but I think we need a better method to actually go and, I wonder if we just did plot.imshow. Plot.imshow, and then if we went and substituted this over here, I'm going off on a tangent now. Self.getObservation. And remember, we need to grab the first value. And if I got rid of this, what's happening here? Doesn't like it. Not a value. Supported values are accent. Does not like that. Oh, now I really want to get this done. All right, so self.cap.grab, self.game location. And then I thought that would work by itself. Boom. What's that error there? Oh, we need to convert it to a NumPy array. Element-wise comparison failed. Plot.imshow game np.array self.cap.grab self.game location. What are we actually doing in here? So we are going, grabbing first 3 channels should still work. It's not a valid name for supported values. I don't know. Doesn't seem to want to work, that render. I reckon let's go back to the cv2.imshow, although I'm not all that happy with the way that that works. I would definitely go and tweak that. So this works, it just hangs massively. Like it'll return that. If I go and run render again, it's not, oh, sorry, it is changing. I just don't like it. It's not the nicest render. Do you know what I mean? Like it's a little bit janky. What about if I brought this? No, so it is working. Okay, we're going to accept that. It works. The close is not that great. All right, let's go and run the render again. All right, so you can see it's definitely working. It's just a little bit shaky because OpenCV doesn't like being in the background. But anyway, all right, so we've got that working-ish. I'm going to take that as an ish. Can definitely be improved in the future, but you saw that matplotlib was not playing all that nice. OpenCV's okay, but it doesn't move all that great. And I believe that's because we're actually working inside of a Jupyter notebook. If you did this in a random or a separate Python script, you should be okay. Okay, but that is that done. The next thing that we're going to do is just make sure we can close down this frame. So we are going to run cv2.destroy all windows. So that will close the render function. So you can see that we've got our little render boy over here. Boom, boom. So that's rendering. Now if we run env, oh, my head's probably covering that. If we run env.close, there you go. So that's destroying that. All right, so it's not that bad. So if we run env.render, env.close, env.render, env.close. All right, I'm going to take that as a win. That looks okay. So if we go and bring our Chrome Dino over to here, so if we run env.render, we'd have our render back there. Yep. env.close. Cool. Bring our Chrome Dino. env render. Boom. env close. All right, cool. That's looking okay. We're going to take that as a win-ish and then go from there. All right, so what else do we have to do? So we've gone and done our render, we've gone and done our close. The last thing that we really need to do is just restart our game. So do our reset function. So what we want is that when we get to this stage, effectively, if you just click anywhere, it's going to restart the game. So we just need to simulate a click using PyDirect input to finish our environment to basically say, once our game's over or once we've detected done, we want to be able to go and reset this game. So we need to go and define a reset function. So let's go on ahead and do this. Alrighty, I think that is it done. So all we're doing inside of our reset method is we're just waiting a second to make sure the game pop up, or we're giving ourselves a second to actually go and reset. Then what we're doing is we're just clicking somewhere up here and then hitting spacebar. And that actually is going to be what our reset method actually simulates. So then when done, we go and click up here, hit spacebar. That is effectively what our reset method is going to do. Okay, so we're done. Let's bring this over here. And let me zoom out just a wee bit so you can see what I've gone and written. So I've gone and written 3 lines. Let me zoom in. Or I've zoomed out and then I've zoomed straight back in. So I've written time.sleep1, and this basically says sleep for a second. And then we're saying PyDirect input.click. So we're going to be clicking up in this region. So X150, Y150, somewhere around here. And then we're saying PyDirect input.press space, which kicks off the new game. And then we're going to be returning the next observation. So return self.get observation. So if we go and create an instance of our web game, and then if I type in env.reset, so right down here, env.reset. There you go. That's resetting our game. So I didn't click. It actually just went and reset our game. All right, let's bring our notebook back up. So if I go and run env.reset again, waits a second, clicks, and then kicks it off. Cool. That is our game effectively now working. So we've now gone and built an entire custom environment. I know it's a little bit sketchy, me trying to put the frame over there, but I sort of wanted to show you how I actually built this originally. That is our environment. And that's what it takes to build a custom environment for custom games. So this is obviously a simple game. You can imagine how hardcore this actually gets for way more complicated games. So we went and defined, let me zoom in to 150. So we went and defined our init method, and inside of that, we set up our observation space and our action space. We then defined our step method, and this is what happens. It's effectively what to do with our game. We created our action map. We created our get done functions, our get observation functions, which are down here. We also set up our render method, which is a little bit janky at the moment. I'll admit, could definitely be better. But I think that's because we're doing it inside of a Jupyter notebook rather than just a straight Python notebook. We also implemented our close method, which closes down our observation method if we use render. And then we went and set up our reset method, which effectively moves over the screen, clicks, and then hits spacebar to kick off a new game. So that is our environment now done. Is there anything else? That is it. So now what we can go on ahead and do is test out our environment, which we've pretty much already done, but let's go and do it again. So we can create a new instance. So to create an instance, we type in env.webgame. Then what we can do is type in or get our observation. So observation equals env.getObservation. And we can use plot.imshow to visualize that, which does not like that. What do we need to do? Oh, we need to get the first value as well, don't we? Right, so that's our observation of our current frame. Let's move this over to the side. Keep it up here. Boom. Let's get our observation again. So that's our little Chrome Dino. And what we can do is do the color conversion. So cv2.cvt color. And then if we pass through, what is it? cv2.color underscore bgr to rgb. Close that. Right, so we've now got a grayscale observation. So we're looking good there. We can also check whether or not our game is done. So remember, we can type in done, comma, done cap equals env.getDone. Print done, comma, we won't print done cap. So that's saying our game is not done, but that is because hold on, it should have picked up done. Plot.imshow done cap. But that has not picked up that. Let's try that again. Let's just move this over a bit. All right, there you go. So maybe it's because my screen's covering it a little bit too much. All right, so that is clearly detected that our game is done. So if I go and run that, you can see it is definitely printing out true. So ideally, we might want to ensure that when we're actually training this, we actually move this Jupyter Notebook off to the other screen to actually get that. So key thing to note, important when you're actually prototyping. So again, it's hitting true. We can go and print out our done capture. You can see it's got game over there. Alrighty, and then again, we can use PyTesseract to go and test this out. So if I type in PyTesseract.image to string, pass through done cap, you can see it's printing out game or if or whatever. And this is what I was talking about. So like the game over bit doesn't always work, but we know that the game bit is coming out pretty strong. So if I just grab the first 4 values, 4, you can see we're getting game. So we are looking good. Now we can obviously go and test this out in a bit of a loop. So let's actually go and write a typical sort of testing or training step for a reinforcement learning environment. You would have seen me write a ton of these before. So let's give this a crack. Okay, that is our testing loop. So I've written 4 episode in range 10. So this means that we're going to play 10 games. Play 10 games. Then the first thing that we do whenever we're actually testing out or working with a reinforcement learning environment is we reset it. So observation equals environment.reset. Because remember, when we call reset over here, we're actually returning the observation because we're calling self.getObservation. Then we are creating a flag. So done equals false. We're creating a counter. So for our total reward, because remember we get 1 point for every frame we're alive. And then we're looping. So while we're not done, so while we're not dead, we are getting our observation, getting our reward, getting our done value, and getting our info by running env.step. And for now, we're just sampling. So we're just taking random actions on our environment. So it might jump, might duck, might do nothing. We're then accumulating our total reward. The total reward plus equals our reward. So that's from 1 episode or from 1 frame. And then we're printing it out. So I've just done some string formatting. So print, and then I've got the F at the start to format the string, quotes, total reward for episode, and then inside of curly braces, I'm returning the episode number is, and then I'm returning the total reward again inside of curly braces. If I move this over to here now, and let's zoom out a bit so we can see it. just to make sure our OCR actually picks it up. So if I go and run this now, you can see that that is now effectively running. Should run again. So this is me not touching the screen. My hands are here, right? So this is our environment just doing its own thing. You can see it's effectively picking up when our game is over, taking random actions. And that is our environment now done. I know a lot of you have asked for how to actually do this. This is how to do it. So we've now gone and created our own custom environment. You could definitely scale this out. If you had containers or virtual machines, you'd be able to run a bunch of environments at the same time. But in a nutshell, that is our environment now running. And if I bring this over here, let's go back. Let me stop this. So if you actually go and take a look, we are printing out our episode reward. So total reward for episode is 11. Let me zoom in so you can see that a bit better. Total episode for reward, or total reward for episode 0 is 11. Total reward for episode 1 is 13. Total reward for episode 2 is 11, 12, 13, 15, 16, 17. So you can see that we are effectively running pretty successfully. So that in a nutshell is our environment and our reinforcement learning environment now done and tested. Let's jump back on over to our client and have a quick chat.
Alrighty, now that that's done, we can start to train the model. Sweet. You mentioned something about DQNs? Sure did. We're going to use a deep Q network to train our Chrome Dino. Nice, let's do it.
So we are on the home run now. Now, all that we have left to do is set up a callback, which you've seen me write a ton of times before. So I'm just going to copy the code in. And then all we really need to do is build a DQN and train this up. So first things first, let's go on ahead and bring in the stuff to create a callback. And again, this is the exact same callback that I use every time when I'm building a reinforcement learning agent. So if you haven't watched some of the previous reinforcement learning videos, by all means, do go and check that out. So first things first, we're going to import OS. So this just helps us navigate a file path. We are then going to import the stable baselines base callback. And we're also going to import the stable baselines environment checker. So this just makes sure that when we actually go and train our DQN, we have a valid environment. So I'm going to bring those in. And then the first thing that we're actually going to go on ahead and do is check our environment. That looks like we're still okay. So iProgress not found. I think we're still okay. All right. So the first thing let's go on ahead and do is we're going to check our environment. So we can run env checker.check env. And then to that, we're going to pass through our environment. Now I'm just going to move this over to the side and get our Chrome Dino up. Let's just wait for ourselves to die. Okay, we're looking good. So let's actually go and pass through our environment. My head's probably covering this. So env_checker.check environment or check env, and then we pass through our actual environment to that. So let's go and do that. And if this returns nothing, that means that our environment is valid, right? So no errors. So let's double check. So you can see there, no checks, no errors. Looks like we're running okay. Then we can create an instance of our callback. And I know this is a little bit of a pain, me coding on here and having the game on the same screen. If there's a better way to do it, let me know. But hopefully this is useful in the long run. We're going to bring in our callback. This is the exact same callback that I've used in every single reinforcement learning video. And effectively what it's going to do is it's going to save our model into a folder called, or we need to pass through our save path. We're going to save it inside of a folder called train. So just create an instance of that folder and you should be good to go. Boom. Then what we're going to do is we're going to create two directories or two paths to directories. So I'm going to create a checkpoint directory. And I'm going to set that equal to /train. And I'm going to create a log directory and I'm going to set that equal to /logs. And so I've already got a folder called logs in here. So these are some previous runs. I'm also going to give you the checkpoints that I used for the final training model. So I actually trained this overnight. So it got okay. It wasn't the most perfect model. You probably want to train for a lot longer to get a perfect model. Maybe fine tune that reward as well. Okay, so we've gone and defined, what have we gone and done? So we've brought in a bunch of dependencies. We've check that the environment is okay. We've also gone and copied over our callback, and we've gone and set up some directories or set up some directory paths. The next thing that we want to do is actually create our callback. So let's do that. So I'm going to say callback equals train and logging callback, which is this over here. So you can see that's that class. And then to that, we're going to pass through how frequently we want to save our model. We're going to say every 1,000 steps. You could change this if you wanted to. This just means it's every 1,000 episodes or every 1,000 steps. So one frame is one step effectively. Every 1,000 frames, we're going to save an instance of our model. And we want to specify where we want to save this to. So we pass through save path equals checkpoint directory. Close that down. All right, cool. So that is our callback bit now done. I know I went through that pretty quickly, but I've done that a bunch of times before. If you have any problems, do let me know. But for now, that is our callback now done. Okay, that is step 3.1 now done. Now what we can do is actually go to step 3.2, build and train our DQN. So the first thing that we need to do is import a bunch of stuff from stable baselines. So let's do that first. Alrighty, so we have now gone and imported our DQN algorithm. So that's pretty much it. We can import a bunch of other stuff. So our monitors, our VEC frame stacking. But for now, we're just going to use the DQN algo. And if you actually go to the stable baselines documentation and take a look, there's a whole bunch of information on how to actually go and play around with this, how to actually go and spin it up. But obviously custom environments are its own unique thing. Now, I highly recommend you go and have a look at the papers as well as go through this stable baselines code. It actually gives you a ton of information as to how the DeepQ network algorithm actually works. And we've previously done a lot of work with PPO, not so much on DQN, but for now, if you get to test out DQN, see how we go. So let's add a comment there. So import the DQN algorithm. Now, the next thing that we're actually going to go ahead and do is actually train. So we're going to create a model and we're going to instantiate an instance of the DQN model. So create the DQN model. And then to that, we are going to pass through that we want to use the CNN policy because we're going to be passing through an observation from our game, which is effectively our little Chrome Dino. We're going to pass through our environment, which is our web game environment from over here. And then we are also going to specify a TensorBoard folder that we're going to be logging to, which is going to be going to our log directory. And then what else do we need to specify? So verbose equals 1. So this means that we're just going to be logging out our results. We are going to set our buffer size to, what is it? 1.2 million. So this is how many frames we collect inside of our DQN buffer. The buffer underscore size equals 1.2 million. And then we are also going to specify our rate or where we actually start learning. So learning starts, I've set that equal to 1,000. Okay, so let's break down that full line. So I've gone and written model equals DQN, and I've specified that we're going to be using a CNN policy. To that, we are passing through our environment, which is the environment that we just went and built. We're specifying TensorBoard underscore log. So if you actually wanted to go and take a look at your logs later on, every time you create a new DQN or a new PPO model, it's going to log out into this folder, and you can actually go and specify or spin up TensorBoard and actually view that log. It gives you episode rewards and episode length, so a lot of information there. But you also get it by specifying verbose equals to 1. You'll actually see that in the frame. Now, DQN's train off a buffer, so we're actually specifying how big our buffer is going to be. You might need to bring this up or down depending on how much RAM you have on your computer. So I've got, I don't know how much I've got on this, like 32 gigs, I think. Performance, memory. Yeah, so I've got 32 gigs on this machine. Hence, I'm able to get up to 1.2 million. You might want to bring this down. Keep in mind to fill up a buffer that size, it's going to take quite a while anyway. So you might perfectly be okay bringing this down. And then I've specified where we actually start training our algorithm. And I've said that kick this off after 1,000 frames or 1,000 steps. Now, again, you can play around with these hyperparameters as well. And if you wanted to, you can actually go and use Optuner like we did in our Doom video to go and fine tune your models. Oh, wait, no, we didn't do it for Doom. We did it for Street Fighter. You can go and take a look at those as well. All right, so that is our DQN now instantiated. Doesn't look like we got any errors there. Now what we can actually go and do is kick off some learning. Now, I'm not going to run the entire learning rate or the entire learning run for this video. I'm actually going to, we'll train for a little bit and then we'll actually be able to see what it looks like as we're training. And then what we will do is I'll show you how to load up some pre-trained weights and you'll be able to test that out. Okay, so the next thing that we actually want to do is kick off training. So to kick off training, we can type in model.learn and we are going to specify how long we want to train for. So I think for the other model or the final model that I'll show you, I trained that for 88,000 steps. That took all night. So if you extrapolate that out forward, it's going to take quite a fair bit of time if you wanted to train for longer. For now, I'm just going to say 5,000 times steps to be completely reasonable to get this video done in time, but you could definitely go and train for longer if you wanted to. And I highly recommend it if you want to build something that's a little bit more bulletproof. Then to ensure that we save our model, we can pass through callbacks. And we want to pass through our callback from over here. If we close that down, if we go and let's bring our script over to this side. And I'm just going to make it a bit smaller, zoom out a bit. So I've written model.learn, let me zoom in now, model.learn, and then I've specified total time steps equals, let's bring this over here. Total time steps equals 5,000. So you could definitely increase that. And this is effectively sort of like epochs when you're training with TensorFlow or PyTorch. So the longer the number of time steps, the longer your model's obviously going to train for. And then we'll specify our callback as equal to callback. Now, I'm not expecting a very good model after 5,000 at all. After 88,000, it still wasn't even perfect, but it was definitely a lot better. But you'll actually see that in a second. So what we'll do is we'll kick off training. And what I actually recommend is taking this off or taking your Jupyter notebook off to the other side and then starting the training run. So I'm actually going to kick this off. It'll actually hide it in the background anyway. So we can actually start this off. It should go over. That is our model now training. So you can see it's jumping a bunch, dead. It should start a new episode. There you go. That is our model now training. So we'll let this train for a bunch of time. So the full 5,000 steps and we should be good to go eventually. Oh, it almost jumped over. So this is it learning. So we'll let it run and we'll be right back. Alrighty, so I let it train for a little while. So the training actually never started. So, but you sort of get the idea. That is the framework for actually going on ahead and building this. So it obviously takes quite a while. So you can see that the frames per second is only 2 frames per second, which is really, really slow. So I think that there's got to be a better way to actually go and define this, but it is still training. So that is our model at least starting to explore and starting to learn about how to actually go and build up or actually play a lot better. Now, rather than doing this completely from scratch, I've actually gone and pre-trained one, which you can actually go and test out. But that is the framework. So if you wanted to go and train for longer, all you needed to do is go and run model.learn for a whole heap longer, and you'd actually be able to go and kick this off. So I think I actually trained this for 88,000 steps, you can obviously go and train for way longer. It's obviously going to generate a significantly better model. But now what we can actually go on ahead and do is load up our model. So if we actually go and take a look inside of our train folder, so because we never got up to 1,000 steps, it didn't save either. But let's actually let this train for 1,000 steps. So we'll actually be able to see a save effectively. So actually what we can also do is we can drop this to 300, and then that way we'll actually save a model. So let's drop this to 300. I'm going to bring this over here. Just want to show you what it looks like once a model's saved, and we'll train. So rather than leaving learning starts at 1,000, let's say learning starts straight away. So we'll set that equal to 0. And then if we kick this off, we should effectively start training straight away. So if I go and run model.learn again, we are training straight away now. We might have stopped the training. Just go back. We had an error there. What's happened? Do we kick that off? Keyboard interrupt. All right, let's go and kick this off again. So if we go and let me just move this over to this side a bit more. There we go. Okay, so now as soon as we start training, we are effectively training the algorithms. Just make sure. There we go. Looks like it's kicking off again. Let's give it a full 300. So we effectively, or a full 1,000. So we effectively get a couple of models saved. But again, 1,000 is going to be nowhere near enough to get an actually high performing model. So let's let that save. I'll actually let it save one model and I'll show you what it looks like. We'll be back.
5 minutes later.
Alrighty, so that has gone and finished training, that quick training run that I sort of wanted to show you. So you can see inside of the train folder, you've now got models saved at 300, 600, and 900 time steps. So that sort of shows you that the callback is actually working in that particular case. Now we can also view what our model performance is looking like. So you can see our learning rate, the loss. Ideally, you'd want to see that drop over time, as well as the number of updates that our model has actually gone through. Now, before we go through this in any more detail, let's jump back on over to our client and see what's left to do.
Alrighty, Nick, you're gonna bring this home or what? Time to test it out? Time to test it out. We'll give this a crack through the Chrome browser, but keep in mind you could apply this design pattern to just about any game. Let's wrap this up.
Alrighty, so all we've really got left to do is test out our model. Now, what we can do is let's test out our model just with the model that we actually went and trained, which ideally is probably gonna suck, or not ideally, it probably will suck. And then we'll test it out with the one that I trained for 88,000 steps. Now, 88,000 steps is by no means the be all and end all when it comes to training these models. You'd ideally want to train it for a ton longer. But in this particular case, that's what I've trained it for overnight. So to be able to get this out this week. Cool. So what we're going to do is first up, we are going to write a test loop, and it's pretty much going to be exactly the same as what we did here, with the core difference being that we are going to, rather than sampling random actions, we're actually going to use the model that we trained just up here to actually save, or to actually go and play the game. So let's go on ahead and make the updates to this. So we're just going to play one game at a time and kick this off. So let me go and tweak this and we'll be able to test it out. Alrighty, those are the only tweaks that we needed to make. So I've gone and added this line here, which is actually taking in our observation. Let me zoom in. Are we zoomed in? Zoomed in? Yep. All right, cool. So what we're doing is we're taking the observation that we originally got back from resetting our environment, and we're passing it to the model.predict function. So model is actually our DQN model, right? If we actually take a look. So you can see that it is our stable baselines DQN model. So that is our DQN model right there. So we are taking the observation that we got from that model and we are passing it through to model.predict. And what we're going to get back from that is the action. And then this, I can't remember what the second bit is. Let's try that up. So do we have an observation? We do. All right, let's try that. Model.predict, pass through our observation. So you get 2, and then I can't remember what the second value is, but you do get something back from that 2 values. So what we actually need to do is unpack this. So we need to get the action, and then get that second value out. So all we really need is the action. So that action is going to be what we pass through to our environment.step function, because remember, our environment.step function is what actually takes an action on our game. Then I've added a sleep between taking actions, and I've added a sleep between games as well. So that's the only real change that I've added there. So now if we bring this over to the left-hand side, we can test out our model. So let me zoom out a little. So this is our agent actually playing. If we go and run this, this is our agent actually playing in real time. So right now it doesn't look like it's doing very much. It's just running straight into it. And that's our agent actually going and running through. So you can see that the reward that we got for that episode is 27. So not all that great. Now what we could actually go on ahead and do is load up one of the pre-trained models that I've got. Now, in order to load a pre-trained model, I've got some of these inside of my folder called train_first. Now, I've also got these available on GitHub, so just keep that in mind. So if you go to the Dino AI folder, I've got this best model.7zip that you can unzip. So you need to un7zip it, and then you'll be able to load it up into here. So I had to compress that a little extra to get it to fit. Okay, so I want this one. So to load, I'm going to load the 88,000 one, which is over here. So I can type in model.load, and then we are going to pass through the full path to that specific model. So os.path.join, and then we're going to go into train first. And then we want best_model. I didn't actually check how this was performing this morning, so who knows, it might still not be all that great. But if you train for longer, the performance improves drastically. So just keep that in mind. Do we need to include .zip? We don't. Okay. Right, so we've now gone and loaded our model. So if we now go and try playing, bring our Chrome Dino back. Let's see how this performs. Not all that great. Let's try doing, I wonder if it's actually gone and loaded it. So DQN. Let's pass through the full file path. Let's get rid of that. There you go. So you can see it's at least jumped over one. Let's let it run for a little bit longer. Let's actually give it a couple of steps to run. Let's play 10 games. There you go. One. Nope, not getting over the second one. All right, it's getting over one at least. This is quite poor performance, guys. One. So it's got over two. I wonder if the sleep is making it suck a little bit. Hold on, let's remove the sleeps. Let's try that again. We can also test out another model, see if those are performing better. There you go. There you go. There you go. Hey. Hey. Oh, it's all right. It's died on 98. But you can see it's at least learned a little bit better on as to how to actually go and play the game. All right, 104. So that 444 high score there, that actually happened last night during training this model. So it's definitely able to learn. There you go. Come on, just a little bit further. There you go, 183. So you can see the model has definitely gone and learned how to play this a whole lot better. Obviously removing those sleeps allowed it to perform a little bit better. It's not always going to perform amazingly every single time, but you can see it's definitely playing the game. It's getting there. It's able to jump over. I don't think it ended up training with the bird, so I wonder how it would actually interact if it actually got some birds flying at it, but you never know. It's not bad. All right, 261, not too bad there. So you can see it's learned how to play the game. That was with 88,000 steps. So I'll obviously give you the fine-tuned model for this, so you'll actually be able to test this out yourself and play around with it. But that sort of gives you an idea as to how you can actually go and build your very own reinforcement learning model for just about any game. And you can obviously extend this out, train it to play a whole lot better. You're just going to need to fine-tune the reward that you actually give your game. But that in a nutshell is that over and done with. So we went and did a ton of stuff. We went and built our own custom environment. We went and trained a model. We went and saved a model. Hopefully you found this a little bit useful, guys, and I'd love to see what games you eventually end up applying this to. And let me know if you end up training this for a whole heap longer. I'd love to see what the performance looks like. It's performing not too bad. That's 200. Oh yeah, come on. 300. Dream run, come on. $424. So you can see it's definitely getting there. It's obviously performing a lot better. It's learned how to jump over cactuses. So I'm going to call this a reasonable level of success, but we could obviously go and take this a whole heap further. It's not letting me, let me move this over. We're going to call that a success. So you can obviously see the rewards are being logged out there as well. So we had 178 on that last one, which doesn't necessarily equate to the 444, but this is our own reward function. So again, we did a ton of stuff. Went and built up our model, installed our dependencies, built our custom environment, which is the hardest bit out of all of this. And then we went and trained our DQN model. And again, I've gone and put all of this code up on GitHub so you can test this out and try it out yourself. Thanks again for tuning in, guys. Peace.
Thanks so much for tuning in, guys. Hopefully you enjoyed this video. If you did, be sure to give it a big thumbs up, hit subscribe, and tick that bell and all that good stuff. And hopefully you enjoyed this reinforcement learning tutorial, because it is quite a powerful skill. You can now take this and sort of start applying it to different realms, to different games. Let me know how you go. If you do apply it to some other games, I'd love to see your results. Thanks again for tuning in, guys. Peace.